Okay, so let's see where we are now. Okay, so you have to stop me at 10:30, so you have 15 minutes to take the quiz. Oh, you can't see anything. I was thinking you were actually seeing what I'm seeing, but no. Okay. Oh. You must have caught some weird app with that. Okay, so here comes the signing sheet. And what you'll note is that we are having an exam on April 11th. And I haven't changed the date of anything, so we're having a quiz today. And then we're having an exam a week later on April the 11th. It was on the syllabus since the beginning of the semester, so it's the same schedule that we've had all semester. So this is the last quiz before the test. But I did post the answer key to the quiz that you just got back. Here comes the signing sheet. All right, so let's take a look at the answer key to the quiz. So, I guarantee you will see a question like this on the exam. It's a very simple question that I could ask, and something that is very useful for, if you're trying to do pH and you've got a concentrated acid or concentrated base, you should be able to do this. It's just a definition of what pH is. This one, if you know what pH is, then you should be able to give me pOH, because you have the equation pH plus pOH is equal to 14. So then you should be able to give me that. Some people did the thing where they took the negative to mean that this is not pH 2, but pH negative 2. And then when they did this, they added instead of subtract. So when they did the calculation for pH, they did not subtract from the 14, they added to it, so they ended up with 16, pH of 6, pOH of 16. You have to watch for the signs there. What's the this another thing that everybody should be able to do? What's the conjugate base of the acid? So if you have HNO3 or H anything, then you just pull the H off, and then that's the conjugate base. In this case, we had the other version had HCN. So if you pull the H off, then what's the conjugate base? CN minus. The pH is negative log of anything. Same question on both. Give the structure formula of one strong base and one strong acid. So, you just, you could have written almost anything there. What I was looking for the equation for Kw is this equation, H3O plus times OH minus is equal to 1 times 10 to the negative 14. Some of you gave me the pK and pH plus pOH is equal to pKw equation, which is fine. That really should have been the only thing that you should have put into that thing. A lot of people this time got the ICE table pretty fairly, almost everybody did pretty well on the ICE table. The only thing that you had to do for completing this question was just complete this part, the part that I have circled. You didn't have to do this for this quiz, but do keep in mind, you do have more time on a test. So it would not be unreasonable for me to go ahead and ask you to do the calculation and come up with a final number. So I did show you how you get the final number, so you have an idea of how to do that. So almost everybody did pretty well on this. This part was worth 3 points. This one was worth 2 points, and then I had a stray 1 point for I not sure what the 1 point was for, because it had 6 points here. But if I take a half a point for each of the little blocks, then this comes out to 3 points. So on this one, almost everybody got the extra credit wrong. But this was a polyprotic acid, so you pull off the first H plus, and then the remainder of what's there. So if you pull off one H off of H2SO4, you get HSO4 minus. And then I meant the same, meaning that you had to write that twice. So there were 4 points, but there were 5 spaces, but these two were the same. And then if you dissociate it one more time, then you get the second H coming off, and then the remainder. So the remainder of the thing that's left after you pull off that second H is the SO4 minus. So the other version had, I just changed some numbers between one version and another version. And then the polyprotic acid that I gave that class was H2CO3. So there are 2 hydrogens on the H2CO3. You pull off one hydrogen, you get HCO3 minus. And then this is the same as that. And then you pull off the second hydrogen, then you get CO3 minus 2. So that was the extra credit. Almost nobody got the extra credit correct. I didn't think it was that difficult, but that's how the cookie crumbles, I guess. So I did post the answer key to this on Brightspace. So where in Brightspace would that be? That would be, okay. This is mine. Here's the Brightspace. Okay, so I posted it on exam keys. So if you go to course home for your Brightspace. And the reason why I mentioned this is because it is very important that you know how to do the problems that show up on the 2 quizzes prior to the exam. So quiz 5 and quiz 6, you want to be able to do the problems that showed up on those quizzes, because they will show up on the exam. Will it be exactly the same question? It will not, but it'll be kind of similar. So here is where the exam keys are. Okay, so quiz 5 key, it's down here. Here's quiz 5 key. So you have access to the answer key to all the quizzes and all the exams that we've taken all semester long. So you should be able to look at those. And what you want to do is you want to make sure that you know how to do that kind of problem, because you'll get a similar problem on the test. So you want to make sure you can do all the stuff that shows up on quiz 5 and quiz 6 before you take the exam, and then you should do pretty well on the exam. So this is where you find the answer keys. So do look at the answer key. You want to compare your answers against the answer key answers. And then what you might want to do is cover up the answers and see if you can still answer the question without looking at the answer. Because just looking at the answers, you'll look at it and say, oh yeah, I understand how that works. And then you'll think that you know how to answer the question. And then you'll find that maybe you don't know how to answer. It takes a while for it to show. It's still in the process of showing up on the, it's a little, oh, there you go. Okay, so it has on there how many points I took off for common mistakes and things like that too. But what you might want to do is, for instance, on this one, you might want to look at the number 0.01. The wireless is slow today and is spotty. Really? Right. Oh, it's taking a really long time. Oh, boy. I'm gonna stop it and then restart it. Here on this happens. Oh, there you go. All right, so here's the answer key to the quiz that I posted. So you want to look at the answer key, make sure you can do the answers for both the versions of the quiz, because I don't look at it and say, oh, let me give the same version that I gave, the first time you took the quiz. Obviously, I can't even do that. So you want to make sure you can do both quizzes. So the quiz that you'll get today and this quiz, and make sure that you can do it before you get to the quiz. All right, so let's continue along. This is where we left off. Did I hand out 15.1? I did not. Okay. Then I probably have 15.1 here. Did I say I had not printed out 15.1? That's possible. Let's see. I didn't. I did not print out 15.1. Oh. Okay, so I actually printed out 15.2 because I thought I had already handed out 15.1. So we'll have to do it without actually having the paper in front of you. I'll hand it out next time the class meets. Oh, I still have some exams from last time. All right, so I did not print this out because I thought I already handed it out. So go ahead and let's do it without actually having a homework paper in front of you. So you can still do it. There's not really that much material to write on there. So you just have, let's go ahead and do it. So what we're doing is we have silver chloride solid, and it is dissociating to give silver ions and chloride ions. And the question says that you're supposed to calculate the molar solubility of the silver chloride in water. Okay, so how would you do that? And then there's a little chart. So this is like an ice chart. The only thing is for the solid, you don't write anything down because it's a solid, so it doesn't actually show up in the KSP equation. So what you can do is, if you don't know what the concentration is, you can just write, so the original would be 0 and 0, and then you can say plus X and plus X. Then you can write out an equation for KSP. So KSP would equal to concentration of silver ions and concentration of chloride ions. And then the silver chloride you would leave off because silver chloride is a solid, so it doesn't show up in the KSP equation. So that's my KSP equation. So I'm just going to plug in the X into the KSP equation. So this is just like a regular ice problem. So we're just going to say, and we're given the value of KSP, we're given 1.8 times 10 to the negative 10th for KSP. So you can say X and X. And then it should be pretty straightforward to come up with the value of X. So the value of X is the molar solubility of silver chloride in water at 25 degrees Celsius. So then you say 1.8 times 10 to the negative 10th is equal to x squared. And then you just have to use your square root button on your calculator. So you get 1.8 times 10 to the negative 10th, the square root of is equal to x. And then you should be able to get the number. I believe I have the answer on the next PowerPoint. There you go. So you plug it, x squared is equal to 1.8 times 10 to the negative 10th. Punch the x squared button on your calculator, square root button on your calculator, and you get the solubility of silver is 1.3 times 10 to the negative 5th. What's the solubility of chloride? It's the same because it dissociates in exactly a 1-to-1 ratio. So the 1.3 times 10 to the negative 5th is equal to the molar solubility of silver and is also equal to the molar solubility of the chloride ion. So that's how you solve this problem. Okay, and I don't have the printout for that because I thought I already had handed it out. And I thought we had already done that one problem. Okay, so next. So this is another case where, in this case, you're actually adding in a certain amount of the counter ion. So in this case, you're going to sort of have to use Le Chatelier's principle because it says that you have barium sulfate in pure water and you want to compare the solubility of barium sulfate in water versus the solubility in 0.10 molar of the sodium sulfate. Of course, the sodium sulfate is the common ion sulfate. So you're going to have something for the concentration of the sulfate ion. So if you have a common ion, if you add to this side, it's going to drive the equation this way. Well, we can actually do a ICE table for this. So we're starting out with 0 amount of the dissociated barium because we're looking at the equilibrium of the barium sulfate dissolved in water. So you're assuming you start out with 0. There's nothing under barium sulfate because it's a solid, so it doesn't actually have a concentration number. And then we're starting out with 0.10 molar of the sulfate because it said that that's how much you added. You added 0.10 molar of the sodium sulfate, so you have 0.10 molar of the sulfate. So this is my initial. So what's the change? The change is going to be plus X and plus X because you're having some of the barium sulfate dissociate to give you barium and sulfate. So what do you have at equilibrium? At equilibrium, you would have X because you started out with 0. 0 plus X gives you X. And it would not be 0 minus X because who would subtract, where would you ever take a 0 and subtract something from it? Because then you get like a negative concentration and that's, there's no such thing as a negative concentration. So you have to actually add it, otherwise it doesn't come out right. In this case, it's a 1-to-1 ratio. So then you're going to say 0.1 is what we started off with. And then I have to add X to get to this value. And then you can plug it into the equation for KSP. So X for the barium and 0.1 plus X for the sulfate. And that's equal to the value that you have for KSP. Now, if you look at the KSP, it's a very small number, meaning that the amount of X that you get is not going to be very large. So then you can say that X is much smaller than 0.10. And this is true for all weak acids, weak bases, and almost all, I think, all KSP equations. It's always a small number. So then you can say X is much smaller than 0.10, unless this concentration is so small that you can't really, even if you produce a very tiny amount, it makes a difference. If you have a small KSP like this, you're not going to get enough of the sulfate produced from the dissociation to have any kind of an effect on a 0.1 molar solution. So then this equation becomes simpler, and it just becomes x times 0.1 is equal to 1.5 times 10 to the negative 9th. And then it becomes an even simpler problem, because then all you have to do is you take the x, 1.5 times 10 to the negative 9th divided by 0.1, and then you get x is equal to 1.5 times 10 to the negative 8th. And you can see from the result there that x is much smaller than 0.10, because x would be 0.000000000015, 8 zeros before you get to 15. So it's a very small number. So outside significant number range for the 0.10 concentration. Okay. So here we have another problem where you're going to do it, and I do have the handout. This one. So I do have an extra credit problem on here. Going to the stuff that's on your it's on the majority of the problems that I had on that. There is one on the page. So I don't think I gave. See if I can read in my table. Can't remember. I made it up this morning, but I still can't remember what I put on it. I didn't give you an ice table, but you still have to do something sort of like what we're doing now. What? Do I have a Oh, yeah, I do have calculators. We are having a quiz. You're not allowed to use a cell phone for a calculator on a quiz. So I do have some calculators. Raise your hand and I'll come around and send them out. I have 2, 3, 4, 5, 6, exactly 6. Thank you. Okay, who else needs a calculator? Raise your hand if you need a calculator. I have the calculator that doesn't have memory, but you can still use it. You just have to go through and look more than otherwise. Okay, so let's take a look at this problem. Okay, how would you handle this? You do know that on the final exam, you are allowed to have a 3x5 card for each of the 3 tests. So you would have 3 3x5 cards plus the one that you come up with after the end of exam number 3. But you're not allowed to have like an entire sheet or anything like that. But you are allowed to have at least 4 3x5 cards. Okay, so let's look at this problem and see if you can navigate what to do with it. Okay. So what we're going to do is, all right, so first we want to read the question. So it says, write the ice table for this solubility product reaction and give the solubility of copper ions and bromide ions. And this is copper +1. And you're to assume that you've added, and this is just like the problem that we just had just a minute ago, you've added 0.20 molar of the sodium bromide to your copper bromide dissociation equation. The value of KSP is 6.3 times 10 to the negative 9th, and you're supposed to get the value of X, where X is what you put into your ice table. All right, so what we're going to do is none of these are going to have anything for copper bromide because that's a solid, so we don't actually do a concentration for that. We're going to say we start out with 0 of the copper ions, and then we're also going to say, it says we have 0.20 molar of the bromide ion. So we're gonna write that down. So it says sodium bromide. There's nowhere else where the sodium would show up, so you're not gonna put anything down for the sodium. But you do have a space in your block for the position of the bromide ion. So there you go. All right, so what do you have what's the change? So you're not gonna subtract an x from 0, because then you'd end up with a negative number, or you'd end up with negative x. So you're gonna have to add x to the copper. You're dissociating copper bromide, so you're gonna form some copper ions. And then you're gonna say the change for the bromide is also plus x. So then what do you have at equilibrium? At equilibrium, 0 plus x just gives you x. 0.2 plus x gives you 0.2 plus x at equilibrium. So then what do we have for our KSP equation? KSP is even easier than equilibrium expressions or Ka or anything like that, because all you do is you just write down copper. Oh, this is +1, copper plus, bromide minus. So that's your KSP expression. That thing is frozen. Why is that thing frozen? Oh, come on, unfreeze. Oh, okay, it unfroze. Because I had my hand there like 5 minutes ago and it's still there. Okay. All right, so we're gonna plug in. So we're gonna say 6.3 times 10 to the negative 9. And then we're gonna say x, and we're gonna say 0.20 plus x. We're gonna make the assumption that plus x is so tiny that we don't even need to bother. So then we're gonna say that this is, let's say this is actually equal to 0.2 because x is much smaller than 0.2. So that's the assumption that we made. So we can go ahead and plug that in now. So then you get 6.3 times 10 to the negative 9 is equal to x times 0.20. So then it becomes a very simple algebra problem where you got 0.20 next to the x. You want to get the x by itself. So you divide both sides of the equation by the 0.20. And when you do that, you get x is equal to 6.3 times 10 to the negative 9 divided by 0.20. You stick that into your calculator, punch the number through. I don't think I actually gave the final answer for this, but you just stick it into your calculator. You have to know where the exponent part on your calculator shows up. Other than that, it's pretty straightforward. And the number that you get would indeed be much smaller than 10 to the negative 9th. It would be like 10 to the negative 8th or something like that. So it would be a pretty small number. I don't think I gave you the answer for this one. I know I gave the answer for one of these. I don't think it was this one. Oh, going too fast. Okay, so all I gave for this is the ICE table. So the ICE table matches what we have here. I gave the KSP value, but I did not actually come up with the value of X. So you would just put into your calculator let me go ahead and do that calculation. So 6.3 EE 9 negative divided by 0.2 gives you, all right, so this comes out to equal 3.15 times 10 to the negative 8. So that's the answer for that. Okay, so let's look at the next thing that I have for for my ICE table here. So got this one. Now this is a slightly more complicated ICE table because you have calcium hydroxide that has 2 hydroxides per mole of the calcium hydroxide. So then when you dissociate it, it gives you 2 of the hydroxides. So then if you get 2 of the hydroxides, that means when you write out the K equation, you're going to have the OH squared. And then if you write down X for calcium +2, that means for the OH, it's not going to be X. It's going to be something other than X because 1 mole of calcium. If you have 1 mole of the calcium hydroxide, you get 1 mole of the calcium, and you get 2 moles of the hydroxide. So you actually have to take that into account. Okay, let me go ahead and head that one out. So we're doing so many ice tables that, you know, when we were doing ice tables initially, said, oh my gosh, what the heck is this? How do we do this? I bet by now it's like, oh, another ice table. I know how to do that. And actually on the last quiz, you all did very well on the ice table. All right, so let's go ahead and do this. So I want you to give me the solubility of the calcium plus ions. So sometimes you'll write the solubility as S instead of X, but you know, either way, so I'm just gonna say, so you're not gonna write down anything for calcium hydroxide because that is a solid, so you don't write anything down for those. But you can go ahead. And so I've given you zeros for both of those. This is not one of those where I gave you the amount of the hydroxide ion that you were adding in. So you're actually calculating it based on 0, starting out with 0 and the dissociation of the calcium hydroxide. So I'm going to say I get X, a change of plus X. Oh, you can't see. Okay, let me, you get a change of plus X for the calcium. And what about the hydroxide? Well, if you started out with 1 mole of calcium hydroxide, you would produce 1 mole of calcium ions, but you would produce 2 moles of the hydroxide because the ratio here is 2 to 1. So if you generate X, then this is 2X. So this is going to be 2X. All right, so what do you have at equilibrium? You just have X and 2X because you started out with 0, or you assume that you started out with 0 and your solid was all you put into your, you put in solid calcium hydroxide into your water. Okay, so then you can write out the equation for KSP. So the equation for KSP would be the concentration of calcium. And then it would be the concentration of OH minus, but it's actually raised to the 2nd power. Why is it raised to the 2nd power? Because we had that thing where you write out equilibrium constant, A moles of molecule A plus B moles of molecule B. Remember that? Where you had A moles of molecule A plus B moles of molecule B going to produce C moles of molecule C, D moles of molecule D, and then you write out the K to equal concentration of C raised to the C power, concentration of D raised to the D power, concentration of A raised to the 8th power, concentration of B raised to the B power. Remember that? So all we're doing is we're just doing that for KSP. So so if this is A and then this is B and this is C, this is where C, little c is 2. So you're raising concentration of C to the C power. Okay, so then we're going to go ahead and plug in the values that you have. I'll give you a couple of minutes. I basically have done the problem. You just have to now add the number in and crunch the number through. So the value of KSP is on your homework sheet. So you've got that written down. So go ahead and see if you can come up with the final number there. So the difference between a quiz and a test is the test, there will be enough time. So if I ask you to come up with the final number, you probably will have enough time to do it. So I think And, am I going, if I ask you for the final number and you don't get the final number correct, and it was a 10-point problem, am I going to take 10 points off from your problem? I am not. If you mostly filled in the rest of the thing and then you did something wrong algebra wise, or you stuck the number, and I've seen people do this, people stick numbers into their calculator wrong and they push the wrong button and they get the wrong number. Am I going to say minus 10? I am not. I'm going to take like -1 and I'm going to say math algebra. Often I can't tell what it is that you did wrong. I just know you set it up correctly, but somehow between you setting it up correctly and you coming up with a final number, you did something wrong and you don't get the right number. So I'll just say math algebra. Subtract off like -1 or something like that. Okay, so you're all working on this, but I think it is kind of important that you be able to actually negotiate doing the final plugging in the numbers and coming up with the final number, because if you're doing a well, I don't know what the plan of the majority of the people in this class are, but if you were doing something like building a building or something like that, and you did because most people who take general chemistry are either going to engineering or some sort of medical field. So, you plug in the number incorrectly and you get some ridiculous number and you say, let's build this building because my calculations show, and then the building collapses because you didn't know how to plug the number into your calculator correctly for the log or something like that. Oh, that would be bad. So I think it is, it's not going to result in you're flunking out of the class, but I think it is something that you should be able to do. Okay, so let me go ahead. By now you should have been able to plug everything in and come up with crunch the number through and gotten the final number, but let's go ahead and do that. Oh, I think I actually have the answer on the next slide, but anyway, let's go ahead and plug that in. So you're going to plug in x, you're going to plug in 2x, and this is going to be squared. So then what do? Well, you're going to have to do the square part. So when you're doing any kind of calculations, what you start out with the stuff that's inside the parentheses first before you start going after other things. So 2 squared gives you 4, and x squared gives you x squared. So now you have on the right side x cubed, which means that hopefully your calculator has a cube root button, because that's what we're going to have to do. So this becomes 6.5 times 10 to the -6 is equal to x cubed times 4. So to get this is a pretty straightforward algebra problem, because you don't have to do much. You just divide both sides by 4. So 6.5 times 10 to the -6 divided by 4 is equal to x cubed. And please don't try to do the entire problem all on one line, because then you get the business of where people take the cube root and then just as if it was the same problem and you can't tell what's going on because you just did the same step in the same problem there. That cube root is equal to x. Okay, there you are. And I believe I have the answer, the final number on the next slide for this problem. Oh, come on. Oh, there, oh, wait. Okay, there you go. All right, so you've got 2x squared, 4x squared, x squared is equal to the thing divided by 2, x is equal to 1.3 times 10 to the -3rd. So, then that gives you the concentration of calcium ions. So if somebody asks you, what's the concentration, what's the solubility of the hydroxide ion? It's not the same as the concentration of the calcium ion, because we said that the solubility of the hydroxide is 2 times the solubility of the calcium, because when calcium hydroxide dissociates, you get 1 calcium and you get 2 hydroxides. So then you have to take this and multiply by 2 to get the solubility of the hydroxide ion. There goes the wireless again. Oh, oh goodness. Blank screen. Let me see if I can stop airplane. Oh, oh, that's surprising. Popped up and didn't show up on my screen. All right, so what happened to my PowerPoint? Were you looking at 15.3? Yes. Okay. So we were looking at, this is what we were looking at. Okay. So next, got another one for you. So this one, and you have to watch out for the, so you look at it and say Hg2Cl2, that must mean that when it dissociates, you get two Hg ions. You don't, because Hg stays together as Hg2, so it stays together as Hg2, 2 plus, and then the chloride comes off separately. So this is similar to the problem that we just had just a minute ago. Not giving me the final solubility. Okay, you're sorry. That's what happens when you walk around in a dark room and you're not careful. Okay, so let's look at this. So we got the ice table. I put zeros there. You're going to put little lines where all the solid is because nothing's going to go in there. And then I didn't even bother giving you the value of KSP because you're not going to calculate the final solubility. You're just going to plug everything into your ice table and come up with a value for KSP. Okay. All right. So we're going to use, you could use S or you could use X. So go ahead and I'm going to let you work on this entirely on your own. See if you guys can do it. You might have to do something like this very soon. I don't believe it's for a solubility problem. I believe it's actually for a acid-base problem, but yeah, similar kind of concept here. I actually gave you a buffer problem on the quiz. Oh, and I realized I forgot to draw a line. I'll Okay, so you're gonna put in some X values. Now note that this has a coefficient of 1, whereas this thing has a coefficient of 2. And that's because of that funny thing where Hg sticks together as Hg2. So that means when you come up with the X's, one of those is going to have a different coefficient. And when you come up with the KSP equation, it's not just going to be the concentrations multiplied together. You'll have to do something else to it. Okay. Are you guys all working on it? I gave you one that actually has. Yeah, I actually did give you a solubility problem, sort of like this one on the quiz. The only thing is that I didn't ask you to do an ice table, but you can do this without writing the ice table, honestly. It's kind of easier if you see it in an ice table, but you can without writing out an ice table. Okay, are you guys getting done here or almost done? Waiting for your quiz with bated breath. Looks like most of you are either done or just waiting for me to come up with an answer. Yeah. All right. So we're gonna say X and we're gonna say 2X because it is a 1-to-2 ratio. So at equilibrium, it would be X. 2X. KSP is equal to mercury. Oops, well, Hg is 8 mercury 2 plus chloride ion squared. Okay, so then I'm going to say KSP is equal to X, so 2X squared. Okay, and I didn't actually ask you to come up with the final solubility number. So, but you could go ahead and solve for X. If I give you the value of KSP, you would be able to solve for X. And this is a pretty straightforward problem because all you'd have to do is take 2 squared, and then you'd end up with X cubed, X squared, and then you'd have another X here, so you'd end up with X cubed, and then you just have to do the calculation, your calculator cube root thing. Okay, so next slide, I just have what I asked you to do, which is just plug in the ice table and plug in the value for the X values into the KSP equations. So that's what we have there. Okay, so next, there are some factors that affect solubility, and these are not the quantitative things that we've been doing. These are like qualitative things that affect solubility. So we have the common ion effect, which basically follows Le Chatelier's principle. The effect of pH, which is basically the common ion effect for H3O plus or OH minus. The effect of complex ions. And the effect of complex ions is there's some ions that will complex with other ions and then it will become soluble. So for instance, silver ammonium complex is soluble in water, but silver chloride is insoluble in water. So if you add ammonia to a silver chloride solution, it will actually dissolve the silver. So then it will affect the solubility. Amphoterism, so aluminum is soluble in both acid and base. So if you have a very acidic solution or a very basic solution, it will be soluble. So this is the factors that affect solubility, the common ion effect. We already did the calculation on this. So this is where you're given the concentration of one of the ions that are involved in the solubility, and then it will affect the solubility. And we already did this problem. But what we're doing there is we're doing the common ion effect, and we're sort of looking at Le Chatelier's principle. So what we did is we're adding more to this side. And of course, you know, if you add to the product side, if you add more concentration to the product side, it drives the reaction back to the starting material. So if you add more to this, it will drive the reaction that way and will affect the molar solubility. So the molar solubility of the magnesium without the addition of the fluoride ion is 2.6 times 10 to the negative fourth. But with the addition of the sodium fluoride, the molar solubility is 7.4 times 10 to the negative ninth. So that's a very significant effect on molar solubility based on you adding one of the products of the solubility equation. So this is just Le Chatelier's principle. So this is the pH effect on Le Chatelier's principle. So this dissociates, calcium carbonate dissociates when you add acidic water to it, and then you generate the calcium ion and the bicarbonate ion. So the water is actually involved in this equilibrium. So this is the effect of solubility, the number, the solubility number, the little x that you have when you're doing these calculations, this x that you got for solubility. So this is the solubility in moles per liter, that axis. The y-axis is the molar solubility. This axis is pH. And according to this equation, the more acidic it is, the more the reaction goes forward, the more soluble it is. The less acidic it is, the less soluble it is. So it has a higher concentration of H3O plus when it has a lower value of pH. So this side is where you have more H3O. This side is where you have less H3O. And you can see that when you go to a higher concentration of H3O, that would drive the reaction this way. The solubility is a lot higher than you have at lower concentration of H3O plus. So that's at basic pH, where you don't have very much H3O plus because you're using the H3O plus and getting it out of the solution. At basic pH, you have very low solubility of the calcium carbonate. So that shows the effect on solubility of the common ion, the acidic common ion by Le Chatelier's principle. Okay, so the complex formation business is, here's silver. Silver forms a complex with ammonia that gives you the silver ammonium complex, which is soluble. And of course, if you remove silver, it's the same as you're removing this. So then it drives the reaction forward because you're removing the silver. You're getting the silver out of here, so it's going to drive the reaction forward by Le Chatelier's principle. And here's the complex ion that you form with the silver that's getting the silver out of the solution. So this silver is a Lewis acid. It's reacting with the ammonia Lewis base. And you get this complex of silver to the ammonium ion, which is soluble in water. So this shows what happens. So this is the silver chloride. It's got some white precipitate down there because it's the saturated form where you've got the more than enough silver chloride, so it's coming out of solution as the precipitate. But if you add ammonia to it, the ammonia reacts with the silver and you form the silver ammonium complex. So now the silver that was the precipitate at the bottom of the beaker has now all this become soluble in the water, so you don't see a precipitate anymore. So it is the effect of the complexing with ammonia to make the thing more soluble than it was before. So the effect of the solubility, so this is the concentration of the ammonia that you're adding. So you're adding more ammonia ions. This is the solubility of the value that you have for the X in your equation here. So if you're adding more ammonia, it becomes more soluble. If you have less ammonia, it becomes less soluble. So in pure water, solubility of silver is around 10 to the negative fifth. At very high concentrations of ammonia, the solubility of the silver is 10 to the negative 1. So it's changed the solubility a lot. Okay, so it's time for the quiz. So I'm all ready for this. And let's see, where's my quiz? Where's the quiz? And I don't think you need a periodic table, but I always give a periodic table. So not a periodic table. Anybody else need a calculator? I still have one more calculator left that I can let you borrow. I don't think there are any typos, but you never know. Okay. So here, let's see. My mouse is- Okay. So here. Yeah. As always, there are two versions. Just wondering if some interesting thing going on. There's always less people going on. Everybody has a quiz, right? You were not. Okay, so I was probably talking and not paying attention to what I was doing. Right, so here's the periodic table. I don't think we need it.